with last class. So we will do some numerical on this. In order to continue with numerical, so let us assume, I will give you some input to you. Let us assume the dead time, just make a note, the dead time of a PID controlled robot link is 0.06 seconds, which is 0.06 seconds. Calculate the tuning parameters for PID what did I say? PID controller. If the time constant is 0.1 second, 0.1 second, 0.06 is the dead time D, and T is 0.1. Calculate tuning parameters for PID control. Just have a look, I will share you the screen. Can you visualize the screen? Okay. So what is given in the question? It is given that your T is 0.1 and then D is 0.6. Okay. In certain problems this is given as D, in certain problems it will be given as C, L, whatever it is, but it is clearly mentioned it's the dead time, right? So for PID, what is the thing? For P, calculating KP, what is the value? Can somebody read out? Guys, are you there?
So T is 0.1, right?
D is 0.1 or T is 0.1. It is 0.06 and see, one is 0.06, which is the dead time. Dead time will be always a very less value, and your total time constant is 0.1 second. Okay. Can you visualize the screen?
Yes, sir.
Yes, sir.
I think it got hanged somewhere. Okay. Now? Okay. Now, what is given in the problem? It is given as 0.06. So, the PID concept one is, what will be the PID in PID concept? What is the important thing? What is the important thing? First thing is, how will you calculate Kp? Kp is how much? 1.2 into, what is the value? T by D. What is the value for this? Which is 1.2 into 0.1 divided by 0.06. What is the value? Can you please tell me? See, it is 0.1 divided by 0.06. It will become 1.6.
4, sir.
1.6
4.
into 1.2. That will become 2 if I am not wrong. So the time constant is 2 in this case. Then what is Ti? Or 1 by Ki. 1 by Ki. That is the integral time constant. What is the value? Can you please tell what is the value? Last class you might have noted, no? What is the value? How will you calculate this? It is 2L. Okay, 2L. Okay, so that is how much? 2L is 2 into L is what? L is basically the dead time. Am I correct? L is the dead time. So 2 times of 0.06 would become how much? 0.12. 2 into 0.06. 0.12. This one is 0.12. Okay, I mean, no need to worry about the annotations. This could be sometimes given as L. This thing could be given as small t. So don't worry about the annotations. So they will mention what is the dead time and what is the time constant. Okay. Now, what is the last one, which is Td? How will you calculate Td? This is 2d. Okay, 2d or 2L. Both are correct. What is Td? How will you calculate Td? Tell me. Td is 0.5L. What is the value? Which is 0.5 into L or T, which is 0.1. What is the value? .05. So using these three parameters, okay, using these three parameters, which is Kp, Ti and Td, we can estimate what is the tuning numbers. Okay, how will you tune the number? So if you set these values as the time constants and the constants in case of proportional controller, automatically the system will perform with the optimized parameters of Kp, Ki and Kd, or Kp, Ti and Td. Both are the same, right? Okay, so let us move on to the next method, which is the next version of Ziegler-Nicholas method. Okay, we call it as sustained oscillations method. We call it as sustained oscillations method. Can you guys, is it audible to you? So in sustained oscillations method, okay, which is the second method, okay, so in this method we start with a proportional controller. Okay, we start with a proportional controller with the lowest possible value of Kp. Why lowest possible value of Kp? Because it will lead to overshoot. Okay, so the biggest potential cause that a system and it will damage the system is, you should select Kp in such a way that it should be as low as possible. Okay, this Kp value should be as low as possible, because the system will become unstable. The system will turn unstable. Okay, first thing is, you assume a plant like this. Okay, given an input R of t, which is basically what kind of signal we have to use? We have to use a step signal. In this case also the step, or maybe we are not giving any signal as such. Okay, or maybe we are not giving any signal as such. We have just taken a feedback loop and given it to a proportional controller. What happens is, since we have started with Kp, okay, what happens is, there will be a sustained amount of oscillation. System will be oscillating to and fro. oscillating to and fro, that means your output will be not stable. Okay, the output will be not stable. You have to measure the period. The period means the time period of these oscillations. So oscillations would be something like this. Okay, something like this. Whenever you get, what do you mean by sustained oscillation? Can somebody tell what is a sustained oscillation?
One which doesn't decay over time.
What do you mean by sustained oscillation? Mahita, can you please tell me what is a sustained oscillation? In signals and systems, or maybe in signals especially, you deal with systems with more repeatability. What do you call such systems, such as signals as? Sustained signals. Am I correct? Inzamam?
Yes, sir.
What do you mean by sustained signal? See, for example, if you are using a mobile phone for talking, okay, so the signal whatever the transmitter transmits into the air and your receiver will receive should be stable. If not, you will get lot of distortion. Okay, such a system is always called a sustainable system and a sustainable control system to be like as a whole. So here also you have to slowly increase the value, okay, of Kp. Why especially Kp? Because if Kp is not increased, what happens? The system would not turn into an oscillatory mode. Okay, so the oscillations or the value of Kp at which you get sustained oscillations is called as Kcr. Okay, Kcr, and the periodic time is called as sustained oscillations period. Okay, sustained oscillations period. Okay, so the output would look something like this. This value might be very low, okay, which is negligible in most of the cases, but this is one of the best methods what in plant you can do, okay, with the systems running in order to get a real time stability. Okay, real time stability. So in this you have to estimate the gains in such a way that you know what is Kcr. Kcr is, it is nothing but the value of Kp at which I got sustained oscillations, and what is Pcr? What is Pcr? Pcr is basically the time period. Okay, it is basically the time period. Okay, and once this time period and the Kcr is identified, what you have to do is you have to start working on this gain estimation chart. Okay, in gain estimation chart, in the first case, since nothing is present, it is basically 0.5 Kcr. Okay, half of the Kcr or half of the Kp. Okay, you should not go beyond half of the Kp. Right. Second thing is in Pi you have Kp and Ti because your Td doesn't exist here, which is equal to 0.45 Kcr and 1 by 1.2 times of Pcr. Similarly for PID it is 0.6 Kcr, 0.5 Pcr, and similarly for TD it is 0.125 Pcr. In examination point of view, you will be given with these two things. Maybe in certain cases you will be given with a diagram. Okay, you will be given with a diagram also. Okay, be careful with this. So can we solve one numerical on this? Right, we will solve one numerical on this. Okay, just have a look. Sustained oscillations. Calculate. So this problem you are going to solve it. Calculate the estimation of Kp and Ki in a PI controller for the following parameters. First thing, KCR is equal to 0.124 and PCR is equal to 0.25 seconds respectively. Okay, because this KCR will not have any parameter, this PCR only will have the parameter because it's the duration. Okay, so what should be the P, that is Kp okay, so consider this as Ti instead of Kp. How will you calculate Kp in case of a PI controller? In case of a PI controller, it is 0.45 times of, which is equal to 0.45. Is it 45 or something else? Yeah, it is 0.45 times of KCR. Okay, which is equal to 0.45 into how much? What is KCR? Can you calculate and tell me what is the answer?
0.0558.
0.0
558.
okay, 558. And what is Ti? Ti is basically 1 by 1.2 into PCR. 1 by 1.2 into PCR, which is equal to, what is 1 by 1.2? Into what is PCR? 0.25, right? So what is
Yes,
the
sir.
answer?
0.208.
0.208.
8.
Okay. Now, if the same thing is asked for a PID controller, can you solve it quickly and tell me the answers? What is Kp, Ki, or it is Ti, Td?
Zero 0.0744.
Okay, so we'll move on to the next part, which is so there are other few names for this method. Okay, generally they call it as bang method. Okay, it is also called as bang method. Right, just have a look. Why it is called as bang method? Any idea? The system is not actually stable. It is moving to one end and another end, so it will bang on one end and it will bang on the other end. Okay, hence the name, right? See, let us have a summary of whatever we have discussed till now. Two things has to be taken away as a review of this Ziegler-Nicholas method. The very first thing is what is the relationship between Kp, Ki and Kd, and how do their response characteristics, okay, how do their response characteristics will vary. First thing is, if I use Kp, I can decrease the rise time. Okay, the rise time is decreased if I am using Kp. If I am using Kd, okay, if I am using Kd or Td, it will reduce. See, there is not much difference between Kd and Td, both are the same, but as a constant it is represented as Td, but as a time value it is represented as Td. Okay, so both are the same, no need to worry. Use Kd to reduce overshoot and settling time. What do you understand by overshoot? As I said, once the output starts reaching to the maximum value, okay, once the output reaches the maximum value or maybe the set point, it will go beyond set point and it will reach the maximum possible value. That maximum possible value is called as overshoot. Okay, what is undershoot? Exactly the opposite. If it is below your set point value and it is going to the minimum value, that is called as undershoot. Okay, these overshoots and undershoots will not exist for a longer time. First thing, it's a kind of jerky thing and it won't exist for a longer time. Next thing is Kd also will improvise, okay, the settling time. What do you mean by improvisation? Is it will reduce the settling time. What happens? You design a motor and you have you design a robotic arm and you have made the motor control for it, and the motor starts wobbling or motor starts moving to and fro. It's an undesirable output. Okay, it won't settle. Settling means to be stable at one position. That is settling. Okay, so that is, see, feedback always will increase the settling time, whereas no feedback will reduce the settling time, because continuous monitoring will be there in feedback system. Okay, so that part will be reduced by Kd. Similarly, Ki, that is the integral time constant, which will reduce the steady state error. Okay, right? Okay, the next one is Ziegler-Nicholas tuning method. Okay, Ziegler-Nicholas tuning rule, okay, or tuning method. At the very first case, it is okay. It's not, so good. For initial process it is fine. Okay, but as the process becomes more complex, you have to go with a sustained oscillations method only. This S-shaped curve is suitable for initial parameters. Okay, but as the thing continues, it won't be good, because if you just have a look in the S-shaped curve, what you could see is you have to give only a step response. But what happens if the system dynamics vary? I cannot give the step response as an input all the time. I have to vary it. Okay, I at times I would give a ramp response, I would give a ramp input, and I will find out the response, and I'll find out the other parts also. But ultimately, what is required is, as the complexity increases, you have to go with only this method. But there is a potential cause of damaging the plant if you are not setting the Kp value. So in both the cases, you require some expertise, right? Any other doubts with tuning of Ziegler-Nicholas method? Coming to twin rotor systems, they are used exclusively in helicopters. Okay, in your drone systems, you have these twin rotors that exist. Okay, it consists of two motors with two rotary blades, blades. The blade count depends upon what kind of application you are using. Okay, if you are planning to use for heavy lifts, your main rotor should be multi-bladed, or it should be more than 3. Okay, it should be more than 3 or more than 2, right? Tail blade or the tail system, okay, will have lesser number of blades. Okay, that depends upon the application. If the thrusts are more, okay, if the balance power requirement is high, in that case also you will go with more than 3. Okay, the central hub in this example is actually pivoted for balancing. Okay, you have a counterbalance our ultimate goal, in order to control this, okay, in order to control this exactly at the axial position, exactly at the axial position. So this should not move, then only you will get a stabilized motion. Okay, so for example, you just assume a helicopter here, okay, a helicopter here that is mounted onto the counterbalance. Counterbalance is the helicopter body. How will the commencement happen? Right? If the forward direction movement has to take place, if the forward direction movement has to take place, what happens? If I tilt this main rotor, okay, if I tilt this main rotor with an angle theta, okay, what happens? The thrust, whatever that is generated, will move in this direction. Okay, in this direction the thrust will be applied, so the locomotion will be exactly normal to it, exactly normal to it, right? Of course this theta is very small, okay, it will be less than 10 degrees, 10 to 15 degrees in most of the cases. It is less than 10 to 15 degrees. Okay, such a low angle has to be controlled. Isn't it a crucial system? Right? If the landing has to happen, what has to be made? This rotary blade has to take an angle exactly perpendicular to the floor. Okay, exactly perpendicular to the floor, and a reduction of RPM, which is omega. Okay, reduction of RPM, which is omega. Here it is considered as angular velocity. Okay, so this angular velocity is reduced in order to make the thing impacted with gravity g, so that slowly it will come down. So this is the function of your main blade. Okay, this is the function of your main blade. Second thing is the second blade. It is also called as the tail blade. Okay, it is also called as the tail blade. So this tail blade will generate the thrust. Okay, which it will generate the thrust. For example, if this is the axis of your body, okay, it will generate the thrust in this direction. Okay, exactly perpendicular to the thing. For forward motion, thrust has to be in this direction. For stabilization, the thrust has to be in this direction. Right? It is exactly, in most of the cases, this is exactly 90 degrees. It will not vary much, except for the rare combat helicopters, it will be used. So in most of the cases, it is 90 degrees. Okay, what is the purpose of this? When certain vehicles like your helicopters and all, when they are rotating in this, for example, this is the axis of the rotor, the primary rotor. When it is rotating in this direction, okay, your omega is in this direction, what happens? The force or the torque that is generated will tend to rotate the whole body, So the amount of torque generated is sufficient to rotate the tail, because the tail part is very small, right? Tail part is very small in terms of its weight or the mass. So what happens? It will also rotate in this direction. Okay, if the tail blade fails, okay, most of the cases it will lead to lot of accidents. So tail blade should be maintained at a variable RPM. Here this is called as omega 2. Only the RPM is varied. Okay, in order to compensate this torque. Okay, so assume this is located at a point P. Okay, so whatever the twist or the turning angle, okay, the turning angle is possible with this particular omega 2 only. So whenever you are varying this omega, there will be a, what happens? There will be a turn. Okay, so let us assume this point P. So with point P, if I draw a radius, if I draw a curve, this will be the turning radius. Okay, so you got the pitching part with this particular thing. Okay, so that's all pertaining to the twin blade system, but twin blade systems have more impact in control systems when you go deeper into the thing. Okay.